we have Tomasz discussing substrate bridges to Polkadot, the view today. Tomasz?
Hey, Bill. Thank you. Hello, everyone. My name is Tomasz Drwięga. I'm a core developer at Parity Technologies, leading the bridge efforts at Parity. So before I go into the main point of my presentation, describing bridges of Polkadot, let me kind of do a little bit of intro. What do we mean about bridges, or where we are in the stack here? So when we talk about Polkadot promises interoperability. It's basically all about interoperability. And what kind of interoperability do we mean? So first we have cross-chain communication. So having two parachains being able to speak to each other. If we zoom out, we may have cross-ecosystem communication. So we have two ecosystems, for instance, Polkadot and Kusama, both built with Substrate, communicating with each other through a bridge. If we zoom out even more, then we have something that we could call cross-consensus communication, where we connect to existing blockchains or other consensus systems that are already out there. So have you noticed this kind of common pattern on all of these slides? Interoperability is all about communication. And if we, it's all about like being able to speak to one another. And if we talk about communication and speaking, we need to think, what language do we speak to one another? And the answer is, our answer to this is XCM. So there is a really good series of blog posts by Gavin, and I really recommend all of you to take a look at this. And this is a quote from this blog post, which says, XCM aims to be a language communicating ideas between consensus systems. So looking at the stack here, we have XCM on the very top. So that's the language we are speaking. Then a little bit right below XCM, we have transport protocols that connect two chains to each other and make it possible for them to speak to each other. And in this transport protocols, we have, for instance, XCMP. So this is like a direct connection between two parachains. We have vertical message passing, which means going through a relay chain. We have bridges as well, or we have custom relays. And what we connect is parachains, solo chains, and kind of entities living on parachains as well, for instance, smart contracts or L2 systems. So what we are going to talk about, and the way we think about bridges, is a transportation protocol for this language, which is XCM. So that's kind of to set the expectations for the rest of the talk. And essentially what bridge is, it's something that will tell the other chain, we call it a target chain, so the chain that we are trying to speak to, that some event or some message has been sent on the source chain. Okay, the target chain obviously will be interested, like, did this event really happen on the source chain? And the bridge can be implemented in various ways, and we have a whole spectrum of bridges here. So again, I'm kind of making a reference to wonderful resources that we have out there, and there is a really good article called Blockchain Bridges, which has this very nice classification and categorization of different bridges. And I'm kind of stealing the categorization from there on my slide here. So on the left-hand side, we have trustless bridges. In that case, the security of the bridge is as good as the security of the bridge networks. So we are not adding any additional kind of security related component there that usually just lowers the security of these networks, of this connection. And on the right-hand side, we have trustless bridges. So the security of the bridge pretty much relies on a reputation of the bridge operator. If we look at the spectrum in terms of kind of implementation complexity, I would say that these trusted bridges are relatively easy. usually it's just a multisig on both of these networks. They are very much focused more on specific use case, and usually that use case is like transferring some assets, transferring tokens. But they are also very practical, right? So sometimes if the security is not that important for you, you can freely use that, because since they are easy to implement, they are available first. And then when we move to the left-hand side of the bridge, we have non-trivial implementation complexity, and also this very idealistic approach where the security is basically the highest it can be. So at Parity, we are mostly interested in the left-hand side of the spectrum. So we are interested in building trustless bridges, even if it's not that simple. So from the perspective of a trustless bridge, this proving to the target chain that some event happened is actually presenting a cryptographic proof that these events indeed did happen on the source chain. So how do we achieve that? How do we create this cryptographic proofs, and how do we make this trustless connection between these two networks? So I've given a bunch of bridge talks in the past as well, so I'm not going to go that much into details right now. I want to focus on the kind of second part of my presentation here. But basically, if we zoom in to this trustless bridge, we can identify 3 layers. Going from the bottom, we have the trust layer, which is an on-chain light client of the other consensus system. So we need to understand how the consensus progresses on the source chain in order to be able to construct these proofs and verify these proofs. On top of this trust layer, we are building this actual transportation layer or messaging layer. So that's something that enables us to queue messages and then receive messages on the other side. And on top of the messaging layer, we have the language. So for instance, XCM or something more specific to a particular chain that we are bridging to. These components that we are building are available for any chain that is being built with Substrate, or actually for any runtime that is being built with Frame. There is a link to our repository down there. Please feel free to take a look. And from the components that we have a bunch of components that in each layer that you can actually mix and match together. So in the trust layer, what we provide is a light client implementation of Grandpa in case the chain is a solo chain. We have a light client implementation of Grandpa for parachains, which means so in both of these clients, we don't care how the blocks are being produced. Either that can be Babe, that can be Aura, or it can be whatever else. We only care that the Grandpa finality gadget is there. So for the solo chain, the Grandpa finality gadget is running directly on the chain, which makes things a little bit easier. And in case of parachain, the Grandpa or finality is achieved on the entire relay chain level, right? So we can follow parachain finality by being able to verify finality of the relay chain. We have an Ethereum POA or Aura implementation as well available. This is being a little bit discontinued right now, but it's a proof of concept. This is something that we have started with, and it works. And if you have a case to bridge an Ethereum POA chain, feel free to try it out. And the thing that we are planning, and I will go a little bit more into details on my further slides, is Beefy and MMR. So in case of the messaging layer, we have something that is called message lanes implementation. So it's a transportation layer that allows, that enables order delivery, enables delivery confirmations, and also allows multiple lanes that kind of have these properties in parallel. So you can send 2 messages in 2 different lanes, and they will be delivered in parallel. However, messages within the same lane will be delivered exactly in the same order they were sent. Something that we plan for the future as well is a much simpler protocol without all of these features that we have in message lanes, but also with this nice property of being very cheap and very simple. And it's going to be an UDP-like protocol where you simply queue messages. They are delivered. They might be delivered in parallel. We don't really know the exact order, but also you don't get confirmations that they were delivered. So it's kind of send and forget. And in terms of the messaging, the language layer, the dispatch layer, currently we support a subset of XCM, which is substrate-chain, encoded calls. So it's very kind of target chain specific messaging. And what we are planning to work on in the near future is XCM integration to kind of fill that block that I showed in the original diagram of having bridges as a transportation layer for XCM as a language. So yeah, now let me talk a little bit about bridges to Polkadot. And there is a huge asterisk there, because I'm going to talk about a very narrow subset of all of the bridges that are being planned for Polkadot. And these are going to be bridges that I was either personally involved in or my team was involved in. So I also encourage you to check out all of the other projects that are currently building for Polkadot. And the first thing that we've been working on for quite some time is a bridge between Polkadot and Kusama that would be running directly on the relay chains. The use case for that bridge is to allow on-chain entities to communicate and to basically prove that the bridge design that we have works. So the bridge will be quite restricted initially. Mainly, it's going to be used for, as I mentioned, this on-chain entities. As a consequence, for instance, Kusama Treasury will be able to hold and transfer the DOT token. And I'm going to talk about timeline on the next slide. So let me just focus on the next thing that we have planned. So a kind of natural consequence of this, or a next step for this, is when we have parachains on both Polkadot and Kusama, having a bridge running on the relay chain is not the most efficient solution. So what we would like to propose to both Polkadot and Kusama councils is to create a bridge that would be operating on the parachain level. So basically create a parachain for Kusama and a parachain for Polkadot and bridge these two. In this phase, we would be opening up the bridge for regular users and for other parachains to use it as well. We would like to enable XCM communication, so we would like to closely integrate with XCM. And in the future, we envision that this might be extended to include other bridges. This is this bridge hub idea that Gav mentioned on his keynote. Having XCM there would mean that any Kusama parachain could send an XCM message that would get routed to this bridge parachain, then routed across the bridge to the Polkadot side, and then from this bridge parachain on Polkadot routed further to another parachain in the Polkadot ecosystem. Obviously, the cost of sending an XCM message to another parachain or across the bridge is quite different. But having this connection available is sounds pretty exciting. So I've mentioned I want to talk more about this other trust layer component that we have planned, and this is Beefy and MMR. So initially, Beefy was designed to enable bridging with Ethereum mainnet. And I need to mention at least two entities and a few people here for kudos. So first, the Web3 Foundation folks who are working on the Beefy gadget, Alistair and Alfonso, and also the Snowfork team who is working on using that Beefy gadget to build a Ethereum bridge to Polkadot. The premise for Beefy is to allow cheaper verification of consensus, because verifying grandpa is quite expensive if you want to do it on chain. We also want to have a much lighter payload to basically like lower the amount of data that we need to send to kind of obtain this trust layer properties. And also a very good consequence of this is that we have unified data types. So while Substrate is extremely generic and allows every chain to customize their header format, for Beefy, the payload would be exactly the same, no matter what kind of header format the chains are using. So we would be able to speak to many chains without kind of adapting for them, because they will use the unified data types. So what Beefy actually is. So this is an additional consensus round done by Grandpa validators. So it piggybacks on Grandpa. It allows crypto to be customized. So for Ethereum bridge, we are actually using SecP 256K1, which is much faster to verify on Ethereum. In the future, we also plan to include threshold signatures. The proofs would be much more lightweight than Grandpa's finality proofs. And also the payload would be much more lightweight. So we don't even need to include header data. We can include something else. And the something else that we have in mind is actually MMR that I'm going to describe on the next slide, because Beefy together with MMR makes it very efficient to prove finalized and historical data at any point in time in the chain. And as I mentioned, Beefy is this consensus gadget. It's available now in Substrate repository. It's still experimental. We still need to do a bunch of tests before we can roll it out on any networks, but feel free to play around with it. And now Merkle Mountain Range. I mentioned that this is a good companion for Beefy. So what Merkle Mountain Range actually is this kind of a Merkle tree with very efficient way of appending new data. So here on the image, you can see a Merkle tree with 8 leaves, which ends up having 14 nodes in total. And when we add a new leaf, if we would like to kind of create a Merkle tree out of this, we would need to add this artificial leaves to make a full binary tree here to compute the Merkle root, while Merkle Mountain Range is actually a forest of multiple Merkle trees that we still kind of compute a single root from the entire forest. So adding one more leaf here creates this kind of small Merkle tree, 15, 16, and 17. And these nodes 14 and 17 are called the peaks of a Merkle Mountain Range. And the peaks are kind of backed together to obtain a single root hash of the entire data structure. So MMR is actually a frame palette available in Substrate repository. You can enable that for your runtime. What it does, it computes a Merkle Mountain root hash in every block, and also exposes a custom RPC that allows you to verify and generate proofs for historical leaves. Leaf data is customizable. By default, it's going to be a parent root hash, but you can also put any kind of chain-specific data that you would like there. So combined with Beefy, we have this single hash of this entire structure of this MMR. And then without even looking at headers, we are able to prove that something that we are interested in actually happened in the chain, that this MMR structure actually contains some data in the leaf. So what are the plans here? So Polkadot and Kusama relay chain bridge is being audited right now. I think there is like 2 weeks of audit left. And very soon after the audit finishes and we fix all of the findings, we would like to propose this to be rolled out to networks. So we would like to propose this for Polkadot and Kusama councils. Next, we would like to focus on Beefy. So get Beefy on Rococo and get it into kind of production readiness. as a consequence, this will enable efficient bridging with Ethereum through the Snow bridge that I've mentioned earlier. And the next step, or something that we will actually do in parallel, is to move the bridge from the relay chain, or work on having the bridge running on the parachain and having an XCM integration as well to enable this kind of nice use case of being able to speak exactly the same language independently from if you are speaking to another parachain within your relay chain, within your ecosystem, or outside of your ecosystem. And that would be all from me. I would like to invite you to our element room, where you can ask us more about bridges, and also make sure to check the source code of the bridge palettes and also the components that are in the Substrate repository.
Thank you very much, Tomasz. That was a really interesting talk. We know bridges are extremely important in our ecosystem, and it's always really neat to see how they're being developed. We did have a few questions from the audience for you. So one, you had mentioned some limitations for the Polkadot to Kusama relay chain to relay chain bridge. And you mentioned as an example, just holding tokens for the treasury of the other chain. Can you go into a little more detail? What are these limitations? Is it just entities on one chain can hold others? Is it certain extrinsics are handled? Like what are those limitations?
So from the bridge perspective, we could enable the bridge for basically, and we could open it up for any users. That would allow any Polkadot relay chain user or any Kusama relay chain user to be able to hold dots and make transfers on Polkadot. However, a long-term plan for the relay chains was always to have as little functionality as possible. So we don't want to kind of clog the relay chain with all of these bridge transfers. And also we don't want to inflate the state of the relay chain with all of these accounts that are coming from the bridge. So the limitation that we are introducing is kind of artificial, just to have the bridge running. So we kind of limit the entities that are allowed to use the bridge, so that when we migrate to the parachain bridge, there is like less state to be migrated to this new paradigm that would be kind of more open by design, because it would be running on the parachain. Is that a satisfying answer?
Yes. I mean, yeah, you basically put guardrails in, right? Is my understanding, like to limit the usage of it. It's not, but theoretically it could be expanded outwards to do all sorts of other things. Okay.
Exactly.
So we had a question here, which I think it would be interesting to go into. Using XCM to interact with these other chains, do the other chains need to do any work to enable that? Is that something that we do entirely on our own? So for instance, when we have a bridge to some other chain X, we need to have chain X agree that, okay, yes, I will also implement this certain XCM capabilities, or is that something we can do entirely on this side?
So like a full-fledged bridge XCM integration is still being worked on. So I don't have all of the answers here yet, but similarly to how you include an XCM in your parachain right now, you are also defining like, how do you treat particular origins? What do you do with particular XCM calls? Which versions do you support? Like XCM is a language, but many chains can speak only like some dialects of this language. So they don't have to support everything. So similarly with bridges, like XCM has also this like two layers, I would say. One layer is the routing. So we know how to reach from one point to another, and how the origin kind of is translated between these different parachains. So the first goal of XCM and bridge integration is to include bridges in this routing, system where you can actually address a chain that is kind of behind this bridge. And the thing that will be supported, like I think the bridge itself will simply whitelist everything and will simply transport all of the calls if they are not to be dispatched on the bridge hub itself. If they are just like being routed and we just forward it to another parachain, we'll probably not even look at the content. Like, don't hold me accountable for this. I haven't thought it through, but that's my at least initial impression, and we will be definitely aiming for that. And then the receiving parachain can see, oh, this is an XCM message that came through the bridge, so I might treat it differently, or I might do something else compared to what I would do if that was a parachain that is within my ecosystem. Because these ecosystems, even if bridged, they will have different security properties, right? So the security of these two networks are independent.
Yeah, so security actually is a good segue into the next question. Are there attacks that you're concerned about in terms of using this, the beefy bridge? Like, are there things that you're worried about, the other chain sending malicious messages or something, and how do you protect against those?
Oh, sure. There's plenty of possible attacks on pretty much like any layer. So we need to, like, when we are building this on-chain light client, we need to make sure that, for instance, whatever is presented to the on-chain light client is also visible or reported as equivocation. So a possible attack there is we have like validators doing a different thing on the network, but presenting a different thing to the bridge itself. So trying to fool the bridge. And then on the messaging layer, I would say like the kind of the most challenging part is making sure that the fees are covered for the relayers. Relayers are these entities that actually make sure that things that happen on one chain are delivered on the other chain. And we need to make sure that there is no kind of griefing attacks against them, and they are not losing money by just like looking at the messages that are there. So yeah, and the weights, for instance, this is also a challenging thing. So yeah, plenty of stuff to think about.
Yeah, plenty of things to keep you busy.